In magnetic flux, if we include the concept of the direction, so basically the force on the conductor is due to the component of magnetic field that is at 90 degree to the conductor, because let's suppose magnetic field is moving towards right hand side, for example. So this is the direction of the magnetic field, for suppose.
Okay. So if it's at 90 degrees, then sine 90, like, would this be considered 90
Sine,
degrees or like 0 degrees?
because 90 degrees and conductor is placed normal to it,
Okay.
so it will be 90 degree, right?
Yes.
So we will get maximum force at 90 degree. So F is equals to B sine theta I into L, or F is equals to,
So the maximum angle which we can use is 90.
yes, because you know that the cycle of sine 90 is between 0 and 1. So the minimum value from sine we got is 0. Sine 0 is equals to 0. And the maximum value we can get from sine theta is 1. So sine 90 is equals to 1, right?
Okay. So that's why if it's perpendicular, that's why we don't do sine theta because we already know it's going to be multiplying by 1.
Yes, because we are using sine theta because we know it is perpendicular case, and in perpendicular case we got maximum force. So maximum force gives you answer 1 when angle is 90, because when theta is 90,
Okay.
so sine 90, you can use calculator also to find out the value, equals to 1, and cos 90 is equals to 0. Both are opposite. Sine 90 is 1, cos 90 is 0.
Co- Do we use cos?
Basically, right now we are not using it, but just for knowledge, both are like opposite to each other.
Okay. So sine 90 is 1 and cos 90 is 0
Yes,
because of the sine and cos graph.
yes. So both gives you like same variation from 0 to 1, but in opposite values. Because as 0 cos we got maximum value, but at 0 sine we got minimum value. So there is like a phase difference of 90, right?
Yes.
So this is the concept of the magnetic field lines with the direction of the current or the conductor. F is equals to BIL sine theta.
Okay.
Yes. And basically, if someone asks you that how to identify that there is a magnetic flux density, so is there any way, is there any experiment to identify that we got
You
magnetic
just
flux density?
do you just see if there's like field lines, like you sprinkled the iron fillings or something?
Okay. But we are, if we consider the definition of magnetic flux density, so it is the force per unit length on a conductor carrying unit current normal to the magnetic field. So magnetic field is already there, right? So definitely if we sprinkle iron filling, so you will get magnetic field evidence. But how we know that there is a force acting per unit length? So is there any method that gives you force per unit length?
No.
Okay. Basically,
So
if
then what do you do?
we need to consider a magnet, let's suppose a simple magnet, and we need to place on the electronic balance, right? So this is the method
Okay.
or experiment. to determine magnetic flux density.
Did they ask for this in paper 5?
Maybe it will help you in different questions also, because you got practical application, just like we were talking previously, that these are magnetic lines, these are not visible, so we are working mostly on imaginations, right? But with different experiments we can also get evidence that either these forces or these quantities exist or not. Okay.
Okay.
Yes, so for this we need to consider, let's suppose, electronic balance. And on this electronic balance, we consider a magnet, U-shaped magnet, let's
Oh,
suppose.
and then once you like find out that the force is being like it's experiencing a force, then the weight will also like increase.
Yes. So if it experiences a force, so definitely with the help of the force, we got greater value of reading in this electronic balance. So that will give you the idea that force is exerting on that wire. Okay. So it is very simple. When current flows through a conductor, a force is exerted on it, and it will give you a value on the electronic balance. And this is the evidence also that force is acting on the wire. Okay.
Okay.
Yes, and by using Fleming's left hand rule we can identify direction again very easily, because we are talking about the direction of the force. Okay.
Okay.
Yes. Okay, next we have a magnetic field around. Magnetic field around a straight current conductor. So magnetic field around a straight current carrying conductor. So now we have again electric current in a conductor, and that is a simple straight wire, just like we discussed right hand grip rule. So in right hand grip rule, we identify the direction of magnetic field lines. But now we are going to discuss about the value, the formula for that magnetic field around a straight current carrying conductor. So the
Okay, straight current of like a wire.
yes, just like we discussed in right hand grip rule. So there is a straight wire, and it generates magnetic field around it, right?
Yes.
So B is directly proportional to I, like magnetic field is directly proportional to the electric current. And secondly, it is inversely proportional to the distance from the conductor, 1 over X. I represents electric current, and X represents distance of a point from the center of wire. And if we combine this concept, so we got formula B is equals to mu naught over 2 pi I over x. So mu naught over 2 pi, this is the constant value, right? And mu naught represents
Distance of a
permeability
point. Wait, permeable for what?
for free space,
Okay. So magnetic flux density is proportional to current. Magnetic flux density is inversely proportional to x.
which is a distance from a point of center of wire, like how close you are to the wire or how far away we are from the wire. Okay.
Okay. And then is this like a different equation? The B equals to mu naught over 2 pi.
Basically, if we combine it, so you will get we get the value mu naught I over 2 pi x. I just write constant values in the bracket, right?
So like I over x is a constant value?
No, mu naught over 2 pi. This is a constant value.
What is mu naught? Permeability. Like would they give it to me in the question?
Yes, it is given on the data sheet in the paper. So you will get this constant value over there. So right now,
Um,
we are only using wire, and around a wire there is a free space, empty space. So in that empty space we have air. So air is actually the medium. So in air, we got this constant value, and we can use this constant value for calculation. But let's suppose if we are using any other medium, just like in the chapter of capacitor, if we use any other medium between the coil or between the field lines or between any specific topic we are talking about, so then we use different medium. But in normal condition, we always talk about air, right? Because when we perform any experiment, so it will give you experiment in the air surrounding. But if you specially perform some experiment without air and there is some other medium, so this value will be different. But in 99 cases we are using the air medium, so that's why this mu naught value remains the same.
the mu naught value is 4 pi times 10 to the power negative 7.
Yes.
Okay.
And 2 pi is like a simple number. You can use the simple values to calculate mu
I
naught
have a
over.
question.
Hmm.
Wouldn't the 4 pi times 10 to the power negative 7 and like the 2 pi, wouldn't it cancel it out so you'd be left with like 2 pi times 10 to the power negative 7?
Yes, you can either use their direct value, but for mu naught, because sometimes in question they ask some different values to find out or some quantities to compare. So it will
Mm.
cancel out. So you will get value 2 into 10 to the power minus 7. But for especially mu naught, this is the value for uh
Yeah.
yes, in vacuum, like in air or in normal medium when magnetic field is spread out.
Okay.
And
Is
let's
this new in this?
no, basically it is already included, and this is the formula or this is the value for magnetic field only, just like we discussed over here, right hand grip rule. So in right hand grip rule, we only discussed that there is a magnetic field, but we don't know, we never studied how to find out this field in calculation base, number base. We only discussed that we can
Yeah.
identify it. So in this topic,
Yes.
we are actually finding out the formula that how to calculate this value. So we can
So
calculate
this
this
is like
value.
quantity.
Yes, this will give you the quantity of magnetic field. Okay. Okay. Any other question in this magnetic field? Okay, so this formula tells you about the magnetic field quantity, right? And we got
Okay.
constant value for permeability. But let's suppose if you consider the situation when two wires are close to each other, just like this. So
Okay.
in this scenario, we also discuss that magnetic field acts around it. And when magnetic field acts around it, so either we get a force of attraction or force of repulsion, right?
Yes.
But again, in this scenario, we only identify the direction of force. We never identify the formula to calculate the quantity of the force. Okay. So to find out the value of the force on a current carrying conductor, due to another conductor. So if we use
So
hmm,
is this kind of induced because the force is like induced?
basically in this example, there are two conductors, so both conductors exerts force of attraction or repulsion. So basically, one conductor apply force on the other, and the second conductor apply force on the first.
Okay.
So this is the force. So normally we discuss previously that it is equals to F equals BIL sine theta. Okay, so F is equals to BIL. Right now, we are not comparing it with the perpendicular condition of the magnetic field. So we use the concept of BIL. And
So the same concept used here.
yes, but we are just starting from this formula. This is not the exact formula. We are starting derivation from this part.
Do
And
they ask for their
maybe sometimes like for 1 or 2 marks, they ask to find out or to drive the relation for the force on a current carrying conductor due to another conductor. Okay.
Okay.
And we know that force is directly proportional to both current I1, I2. So if I1 increases, force increase, I2 increases, so again force increases, right?
Yes.
So we can say that B is equals to mu naught I over 2 pi x multiplied by I2 into L, right? Because in definition it is written force on a current carrying conductor due to another conductor. So one conductor is exerting force on the other. So if we calculate one value, so same value will be considered for the other conductor, right?
So instead of using B, we use its other formula, which is M mu naught over 2 pi x.
Yes. Because in previous
We
formula we discussed it is the magnetic field around a straight current carrying conductor, right? So we already calculated the value of magnetic field. So that's why we are using the direct value of magnetic field around a straight current carrying conductor. Okay,
Okay, so then we like what's it called? We substitute that
value
equation
of B. Yes,
not over pi x, and then instead of putting I, we put I2, the current from the second one, multiplied by the length.
yes. So we are using the value like magnetic field of one conductor that exerts force on the second conductor. In the same way, second conductor exerts the force on the first. So both exert same type of force, but in opposite direction, right? Just
Yeah.
like in diagram. So we have same force, but opposite directions only. And if we shift L on the other side, so force per unit length is equals to mu naught.
All that I1 divided by 2 pi x times I2.
So again,
Why
mu
would
naught. Hmm,
why would we try to find out F over L? Like, is it worth something?
it is like force per unit length. Like a unit length, on a unit length, if we apply force, so we are going to check that per unit length, force is directly proportional to which quantity. Okay.
We're trying to find out like the magnetic flux density.
Basically, if we not shift length on the other side, so it is not compulsory. Otherwise, if you shift on the other side, so it will give you force per unit length.
Okay. What does x stand for again? Is it the distance?
Yes. Basically, X is like, for example, if you have a conductor
Mm-hmm.
like this, and there is a magnetic field around it like this. And for example, a second conductor is placed at a distance over here. So there is a distance X like this. So from the center of the first conductor to the second
The
conductor.
second.
Yes, so this is actually
Okay.
X. And
Okay.
according to the formula, we again come to know that F over L, it means force per unit length is directly proportional to I1, I2. Because other quantities are constant. Mu naught, 2 pi x, these are constant values. Only it depends upon the values of current,
Okay.
right? So it will help you in some ideas that it directly depends upon the value of electric current. Or further, we can say that even if magnitudes of current are different, the force on both of the conductors will be same because force is directly proportional to the product of both current. So even if the values are different, you will get same force, and this is due to Newton's third law, right?
So if the magnet of current are different than the force of both of the conductors. Wait, so if the current values are different on both the conductors, so then the force would still be the same, even if the current is different.
Yes, because from this formula we derive that F over L is directly proportional to the product of I1 and I2. So if we multiply I1 and I2, for example, if we have current in the first wire which is equals to 2 ampere, let's suppose, and in the second we have 1 ampere. So we will get the product
Yeah.
of 2 into 1, it will gives you 2, which is directly proportional to F. So force increases by 2 times, right? And if we
Okay.
change the value,
Yes.
so again you will get the same product. So this is the basic purpose of writing this description.
Okay. How much is left